This water looks dirty now, but chemistry can clean it using carbon that's full of tiny holes. Hello everybody, I'm Molly, and today I will be taking you through the carbon for water treatment activity. In this, we will complete an experiment that shows you how carbon could absorb molecules. This is based upon the web page in the ChemBAM website linked below. Here's the background. Teachers, feel free to show this as a part of your lesson. Providing clean water for people to drink is one of the biggest challenges in our world. Some countries struggle with waterborne diseases. Others face natural pollutants such as arsenic, or man-made pollutants such as textile dyes or pharmaceuticals. One way to remove pollutants from water is using activated carbons. This is carbon with a lot of small holes or pores and has a very high surface area. The pollutants are able to stick, also called adsorb, and therefore are removed from the water. Activated carbon is usually made from biological materials such as wood, nutshells, peat, or coal. If these are heated in an inert atmosphere, which means no oxygen, they will turn into carbon. However, the carbon that's produced isn't very porous, so won't absorb any of the molecules. Instead, the biological materials are heated to a very high temperature in steam. The steam reacts with the carbon to make carbon dioxide, and very tiny holes are left behind in the carbon. Another option for making activated carbon is using chemical treatment. In this case, the biological material is soaked in acid, base, or a strong salt solution before being heated. This also makes very small pores in the carbon. Despite the range of activated carbon being available, they can also be too expensive for large-scale water treatment. Also, new types of porous carbon are needed. This is not just for water treatment, but for other applications such as batteries or fuel cells. You can find more out about carbon on our webpage linked below. This is the first exercise. Fill a bucket with water and cut the scouring pad off of a sponge, so it's two separate parts, the scouring pad and the sponge. The scouring pad represents the charcoal, while the sponge represents the activated carbon. Add each of these in turn to the water and let them absorb the water for a few seconds. You can then take them out and give them a squeeze. Which one works better at soaking up the water? Why is this the case? Think about it in terms of pollutant molecules being absorbed by either the charcoal or the activated carbon. This is the experiment we're going to complete today. The ability of carbons to absorb pollutants can be tested using dyes. The coloured molecules are easily absorbed onto the carbon and can be easily monitored using the loss of colour from the solution. In scientific research, we use a compound called methylene blue. However, food dyes such as E102 and E133 can also be used. You might also consider combining this activity with another one on the ChemBAM website, which is called Cages to Trap Metal Ions. The link for the webpage can be found below and the YouTube video just up here. The aim of this experiment is to see whether activated carbon or charcoal is better at removing molecules from water. This is what you will need.
Some glass beakers and something to stir it with, a measuring cylinder, some filter paper and funnels, an aqueous solution of various dyes or food colourings. Here I'm using methylene blue solution, some activated carbon and some crushed charcoal.
On to the actual activity. If you are completing this as a part of a lesson, feel free to show this either before or after the students have a go themselves, depending on your class.
Okay, so I previously tried it using these gel food colourings. However, I'm going to save you the time and say that this didn't work that well. So you'll have to try different types of food colouring that contains different ingredients, because this may block the carbon pores in either the activated carbon or the charcoal. So instead, I found some of the methylene blue in the cupboard and we're going to use this instead. It comes as a powder, so I'm going to show you how to dissolve it down, turn it into a stock solution, and therefore dilute this down even further. So first we're going to weigh out 0.1 grams of the methylene blue powder. This is strangely green, however when we add it to the water in a minute it should change colour. Once this is weighed out, you can then add it to 100 millilitres of water and this will make a very concentrated stock solution. It dissolves pretty quickly, so all you got to do is give it a little stir. And then we're going to grab any container and fill it up with a litre of water. We're then going to take 10 milliliters of the stock solution and add this to the 1 litre of water. This should make the perfect concentration in order to add enough of the activated carbon and charcoal to see a difference in the colour change. And that also just needs a very quick stir. So this is now the solution that's ready for the experiment. So now I'm currently weighing out 1 gram of charcoal to add to a labelled beaker. I'm then taking this bag of coconut shell activated carbon and once again measuring out 1 gram and adding it to a labelled beaker. So we now have 3 beakers, the 1 gram of charcoal, the 1 gram of activated carbon and the control, which is currently empty. And I'm going to add 100 milliliters of the methyl blue solution to each of these beakers. I'm now going to stir the carbon added solutions for 5 minutes. You can also put some magnetic stirring rods in these and add them to a magnetic stirrer to save you a little bit of energy. While that continues stirring, I'm going to just label some more tubes. Also, while I'm waiting, I'm just going to filter my control. So if you don't want to hold this, you can use a clamp stand, and I also don't filter the full 100 milliliters just to save a little bit of time. Once the 5 minutes up, I'm going to do exactly the same thing for the charcoal added and activated carbon added solutions. And you can see here that the charcoal and activated carbon solutions are very slightly lighter in colour than the control solution. However, I have another brand of activated carbon, so I'm going to retry this using 1 gram of that instead. This is currently stirring, however I'm going to set up another experiment at the same time. This includes weighing out masses of the activated carbon in a log base 2 scale. So the 1 gram that is currently stirring is the equivalent of 2 to the power of 0, because anything to the power of 0 is 1. And then I have weighed out 2 grams of activated carbon here, which is 2 to the power of 1, and then 4 grams, which is 2 to the power of 2, and then 8 grams, which is 2 to the power of 3, and then 16 grams, which is 2 to the power of 4. At this point where I was adding the 100 milliliters of solution, I noticed that the more activated carbon, the more fizzing that happens when you add the solution. This makes sense because it could be the activated carbon getting rid of all of the air trapped in the pores that we previously spoke about. So after waiting for 5 minutes for all of these to absorb the colour molecules, I then filtered all of them, and this is the results.
This is our control. This was 1 gram of charcoal, and as you can see here, it is very slightly lighter than control. Then I used this activated carbon using coconut shells. That was also 1 gram. And once again, it's very slightly lighter than the charcoal, but once again, not much more lighter. However, I then switched to the alpha aceto carbon activated and still used 1 gram, but as you can see here, it is definitely lighter than the original control. So this is the control, and then this is the 1 gram of alpha activated carbon. And as you can see, this is much darker. This is then my base 2 logarithmic series of how much activated carbon in 100 milliliters of the solution. I then filtered out these amounts so that you don't see any of the actual activated carbon residue altering the results of the colour of the solution. And as you can see here, the more activating carbon, the clearer it is. It gets lighter with 1 and lighter with 2. By 4 grams, it's pretty much completely clear. However, this is definitely emphasised by the 8 grams and the 16 grams. These two just look like solid water. This may be different for different brands of activated carbon and will definitely be different for different food colourings and dyes, shown by how earlier this didn't happen when I used the gel food colouring, but this did work when I got out and diluted the methylene blue. And so once you have a very basic scale like this, you can then test different weights in between, which you can then create a beautiful graph. There are a set of questions on the activity pack linked in the ChemBAM webpage that you can download and complete at this point. So how does this relate to research that is currently happening? Once again, feel free to play this as a part of your lesson. It's easy to see how the colour has visually disappeared from the solution, but it's also possible to more accurately measure this using a technique called UV-vis spectroscopy. The peaks in the graph are where the light is absorbed by the solution. So when 2 grams of carbon is added, no light is absorbed from the solution, resulting in no peak. This is because the solution is now colourless. All the coloured molecules have stuck to the solid carbon. If you want to plot this graph yourself, download the file from the link in the webpage. You can also try to use activated carbon to remove coloured molecules from everyday items. We have tried blue, Powerade, Ribena, and iron brew. We found that a lot more of the activated carbon is needed compared to the pure dye solutions. This is probably because the drinks contain a lot of other molecules, such as sugars and flavours. In the School of Chemistry at the University of Birmingham, researchers working with Zoe Schnapp have been developing ways of making new types of porous carbon from waste materials such as sawdust. The process is very similar compared to those used for making activated carbons. Sawdust is mixed with a solution of iron nitrate and then heated in a furnace in an air-free environment. The iron is dispersed over the woody fibres, and during the heating process, the iron compounds break down to form nanoparticles, or a material called iron carbide. This is perhaps more familiar as one of the components in steel. The iron carbide nanoparticles burrow into the biomass, a little like a rabbit burrowing through the ground. What is left behind is essentially a carbon nanotube, and so the result of the process is a very solid material that looks a lot like charcoal, but is full of very thin, tiny hollow tubes, each one over 1,000 times smaller than a human hair. We can see these using a technique called electron microscopy. This picture is at low magnification. It shows the structure of the wood that is being kept in the carbon. The tubes are what the tree uses to transport fluids. This picture is at much higher magnification, and it shows the tiny carbon nanotubes looking a little bit like tiny strands of spaghetti all tangled together. You can tell from the scale bar that each of the tubes is only 50 nanometers in diameter. An average human hair is 100 micrometers in diameter, so that's 2,000 times larger than the nanopore tube. This research is fascinating, as it is a way of making new carbon materials with really complex structures using a waste material such as sawdust. In the next stage of research, scientists on this project are seeing if the same chemistry works with other biological materials such as straw or nut shells. This new carbon material has some fascinating properties. It contains carbon nanotubes, so it can conduct electricity. This can make it very useful in applications like batteries. It has a very high surface area because of all the tiny tubes, and so it could also be useful in water filtration. Find out more about this research in both the press release and the original paper that can be found on the web page linked below. I hope you've enjoyed this fun activity. Please check out the other experiments, videos, and pupil resources on the website. And if you have any questions, feedback, or would like to request a visit, please use the form in the Contact Us section to get in touch. There are also some other videos that ChemBAM has made, so if you are interested, please check out the YouTube channel page. Thank you so much. Bye!